Okay, so let's go through the two quizzes that were in Canvas. One quiz was multiple choice and the other free response. So in general, on the AP exam, you have about 90 seconds for each multiple choice question. And so while this one wasn't necessarily timed, because I encourage you on some of these little practice quizzes to look things up if you're stuck. I mean, always kind of keeping in mind the time constraint in the back of your head. But this would be, let's see, 90 seconds per question. There were, 7 questions? So I don't know, I would plan on maybe 10 minutes or so. These are all pretty quick questions too that don't require a whole lot of deep thought, right? So here we're just rounding the given number on our calculator to 4 significant figures. The most common wrong answer is actually that 4.501 times 10 to the second. So if you pick that, you're probably in company. And gosh, you were so close. The only difference is that if this would have said something like 4.501 times 10 to the negative second, then yay, happy face. Then that would have been totally acceptable. And in fact, sometimes I kind of like that if I have crazy numbers, either really small or really large, sometimes I kind of like to put them in scientific notation, because then whatever's out in front of the times 10 to the what, then that's just what's meant to be significant. But this one, you just had to be a little careful that the exponent would have been the negative second, not the positive second. So really the only one here that would have still given me 4 sig figs is the 0.04501. Also, I should mention too that in Canvas, the choices may be jumbled. So your choices may not have been in this exact same order, but somewhere you had the same choices. We have to remember our 0 rules for sig figs, in that those leading zeros are not significant. This is something really small, and there's nothing in those leading spots to measure. Or you think of it as, if it's small and if I put this in scientific notation, if I'm going to drop those zeros, then they were not significant. But that 0 that's tracked between the 5 and now the 1, that would be a significant 0. If you never did a lot with sig figs last year, because maybe the pandemic hit and this would have been something that you did, or maybe your teacher rearranged units, let me know if it's not coming for you. It's kind of just a necessary evil, and it's really annoying at the beginning to remember all these 0 rules, but it is expected of us on the AP exam that we're going to be expected to report our final numerical answers properly. And so they're just going to expect that we can round to proper sig figs. But again, if it's something that you're not as familiar with, let me know. I get that it's kind of clunky and weird. Number 2, we're doing a little conversion. There's a couple options here. We were given a conversion between liters and quarts. The number given was in milliliters. So you could have done something like this, and I'm obsessed with canceling units. There's no better feeling, right? Where I've got milliliters on the top, milliliters on the bottom. I could cancel, and now I've switched it to liters. Or if you would rather, as long as you remember the order of those metric bases, kilo, hecto, deca, then comes the regular base unit, which here would be liters. It's like regular grams, meters, liters, then deci, centi, milli. So you could just flip the decimal spot too if you want, where the given number was in milliliters, and I would want to bring it to liters. 1, 2, 3. So I could have just started by moving the decimal spot, boop, 1, 2, 3, so that it would have been 4.301 liters, and then I would have gone liters to quarts. But setting it up this way is also just fine. Liters and liters cancel, and it should be, I mean, intuitively, gosh, a liter and a quart are very similar. A quart is just a tad bit larger in volume. So I'm looking for something that's a little bit larger then 4.3-ish liters. And so quarts, yeah, like 4.559 sounds pretty darn good. Now, with sig figs, you don't have to worry, in this case, about going to 3 significant figures because this 1.06 quarts was in 3, and we're doing multiplication and division. It's considered a constant. The same thing's going to happen when we do stoichiometry and mole calculations, and you start looking at the molar masses on the periodic table. Well, every periodic table reports slightly different molar masses with different sig figs. So we don't use those as constants when we're determining final sig figs. We go with the number of sig figs in the original given data. So the original data, the original measurement was 4,301 milliliters, which is 4 sig figs, and then we can just leave 4 in our final answer. We don't have to worry about like the conversion factor here for quarts, or more importantly, like when we do stoic and moles, we just round to whatever the original given measurement had for sig figs. And we don't have to take into consideration the sig figs on our periodic table. Number 3, we are subtracting. So it's fine if you want to plug it in your calculator, but then remember the final rule with subtraction is that we round to whatever piece of data had less decimal spots, whether it would be subtracting or adding. Now, often this isn't a big deal because, when would I use this with real data? Maybe I'm subtracting a final and initial mass, but realistically in the lab, we're probably using the same electronic balance for our final and initial masses, and then we're going to get the same amount of decimal spots. So something like this would come from maybe somebody that did use 2 different measuring devices or 2 different electronic balances. Same thing might happen if we're trying to do like a final volume and an initial volume. As long as we used the same graduated cylinder, we'd have the same amount of sig figs. Maybe if I were like adding volumes, but I used different measuring tools, then I would add them up and round to whatever measuring tool was the least precise, or whichever one gives me the least amount of decimal spots. Question 4. Indium has a density of 7.2 grams per milliliter. We've been given the mass, and we just want to do a little simple algebra to solve for the volume. But oh my gosh, I can't tell you how many times people have total brain farts when solving for like the volume here. They like multiply across, and I think I get it. That they're thinking about something like this, where here I've got these proportions, and I plug this in my calculator by multiplying any numbers across the top, and I divide by anything on the bottom. But this is a little different. This is an equality. So here I want to cross multiply to solve for volume on the bottom. You can also double check your answer at the end. If you get a volume, plug it back in and see if you get the right density. And so in this case, I would cross multiply, and then finally here I would divide each side by the 7.2. My density only had 2 sig figs, so I can just leave this as 2. And again, if I plug that back in, I should get a reasonable density. I should be close to the 7.2. Piece of cake, right? Gosh, it's so easy. Question 5. A reading of 14.85 milliliters is reported from a graduated cylinder. Which of the following describes the markings? Okay, so in a measurement, the last decimal spot is always our estimate. So that means that this particular graduated cylinder would have had a marking for 14.8 milliliters. So it would have had markings every 1/10 of a milliliter, which then would let me estimate to 100th of a milliliter. So maybe it would have looked something like this picture, where there's a line for 14.8. I'm confident it hits the 14.8. But the 0.85, 0.84, that last spot is my estimate. Cool. Okay, this one was also one that is commonly missed. The image below shows a burette that was used to deliver acid during a titration. And so right now you might be like, what is going on? What's a titration? What's a burette? Okay, well, maybe if you got this one wrong, it's not entirely your fault. I'm going to guess that not many of us got to the acid-base unit at the end of first year chem. I know I did not. Titration is something that we're going to do a ton this year. We're probably going to do like 4 titrations. It's really fun. I hope that we can get you into the lab at some point so you can titrate. It's a laboratory method of determining the amount of acid maybe in an unknown sample. Like, what's the concentration? I'm hoping that maybe you did concentration, like molarity, at the end of the course last year. It would have been like right at the end. And so some of this, again, may or may not be your fault. But what if we had an acid and we wanted to know the concentration? Like how much hydrochloric acid is in a liter of this solution. And so that would be this titration. It's a lab method. Burettes look like a graduated cylinder, and we would usually use them at the end of first year chemistry, but we probably didn't last year. They look like a graduated cylinder. They measure volume. The big difference is that they measure volume delivered. And so the markings are kind of backwards. So normally, like on a graduated cylinder, I would have like down here, this would be like the 15, and this would be 16, and 17 milliliters. Like we would read from the bottom up, like what is the volume present?
Victoria Cassis, please report to student services.
This time, burettes start with a full volume. So you're supposed to fill your burette all the way up to the top mark. The top mark is going to be the 0 marking, which again, that's kind of backwards. Like if I had 0 milliliters, you'd think it would be empty. But here it measures volume delivered. So when you start filling a burette, you're supposed to fill it all the way to the top. And then once I have it to the 0, it means 0 volume is delivered. Okay, well then at the bottom of a burette, let's say I can just extend this a little bit, like bzz, bzz. There is like a little valve and like a little trigger on the bottom. And we open up the valve on the burette and we let the liquid drip out of the burette. So we read volume delivered. So if I start at the 0 mark, it means 0 milliliters have been delivered. Well then, yeah, you'd like open up this little guy on the bottom and you let the liquid like drip, 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 drip. You let it drip out. And so if I didn't, let's say I didn't start with it all the way at 0, which is usually not normal. Usually we start with a full burette. But this person, if I read from the top down, I would be reading like 14, 14.1, 14.2, 14.3, and I think it's right on the line. So I'm going to say their initial reading was 14.3 milliliters. Then they opened up their burette and they let some of the liquid drip out so that their final volume is here as indicated on the bottom. Okay, so now we read the final volume, again, like from the top down on a burette. So this would be like 15, 15.1, 2, 3, 4, 15.5, 15.6, 15.7. I think it's like in between the 15.7 and the 15.8. So I estimated 0.75. Well, now all you would have to do is subtract. You would subtract final and initial, and the difference is the volume you delivered from your burette. Now, good practice with a burette is to start at 0. If I would have started at the 0 mark, meaning 0 volume delivered, then whatever your burette final reading is, then that just is the volume delivered. But there are times, and especially like if we titrate or we do something where we're running multiple trials, if I only have to deliver 5 milliliters, well, instead of like refilling the burette for each trial, we'd probably then just say, okay, so now my initial reading is 5 point whatever milliliters. And then I brought it from 5 milliliters down to 10 milliliters. So I delivered another 5 milliliters. So anyways, don't freak yourself out too much about reading volume on a burette at this point in the game. It's probably something that you did not do last year. And again, it wouldn't have been your fault that you missed out on the acid-base unit in first year chemistry. But hopefully that kind of makes sense a little bit. So if I subtract these two, I should be at about 1.45 milliliters delivered. Now maybe you knew too that it's got to be either the 1.45 or the 16.25, because if I just look at the markings, this measuring tool should be able to read for sure to the nearest tenth of a milliliter, and then I get to estimate to 100th. So I should have volume readings that have 2 decimal spots. Cool. And the last one. This is a great question. This is AP. I mean, some of the earlier questions would have been fair game for a first year kid. Like, hey, round this to 4 sig figs. Okay. This is like another level. I like this question. So somebody is trying to measure, what are they measuring? Density of an unknown liquid by measuring a given volume of liquid using 3 different volumetric pipettes. A volumetric pipette is just a pipette. Like, do you remember those little squeezy plastic pipettes? But it's got little markings on it so that you could like suck up certain volumes. Often we just use kind of generic pipettes in the lab, but there are some that have like little markings on it so you could like purposely suck up 2 milliliters or whatever. The mass of each specific volume of liquid was then measured using an electronic balance. So maybe I sucked up a certain volume and then I like squirted it into like a plastic weigh boat on the electronic balance. So I've got the masses, I've got the volumes, and I've got the densities for 3 trials, but the densities are all too high. The actual density should be 1.5. I'm looking for a reasonable source of error. Okay, so if I think about this, if my density is too high, either my mass was too high or my volume was too low. And so on free response questions, they like to do this too. Like, hey, here's somebody's data, but here's the theoretical mass, volume, density, whatever it is. What's a logical source of error? Or maybe they propose a source of error and say, would this be a logical source of error? And so in this case, we're looking for errors that would either cause my mass to be too high or my volume too low. Poor quality of pipettes is kind of a generic answer, and I don't know. I mean, was it poor quality because they didn't suck up enough volume, or did they get too much volume? I don't know. That's kind of a shot in the dark kind of excuse, not giving me enough information. Some of the liquid spilled when measuring the mass. So somebody maybe had an electronic weigh boat or a little weigh boat on the electronic balance, and they like squirt the liquid in and some of it splattered out, I don't know. But then that would cause the mass to be too small if some of the liquid spilled out of my pan or weigh boat or whatever I was using. The pipettes delivered too much volume. Nope, if the volume was too high, then my density would be too low. So it could have been that the electronic balance was dirty, that maybe there was something else on the balance, maybe some extra liquid, or maybe from another experiment, somebody was measuring a solid and there was already some solid on the balance pan, and then that extra mass was being included in my mass here. Maybe somebody didn't hit the 0 button when they were trying to determine the mass of the sample, and so then it didn't zero out that extra contaminant or whatever was making the electronic balance dirty. So anyways, I hope that this helps a little bit. If there's anything here that is not 100% making sense, just let me know.